Okay, so when we were talking about inverses, we did talk about an exponential function that kind of looked like that, and we talked about what the inverse of that exponential function would look like. And we kind of moved some functions around and moved the points around and kind of graphed what we thought it would be. It ends up being something that looks kind of like this. Okay? That original one was the exponential. Well, this new one, this green one, is called logarithmic. And we do always shorten that to be log. And so if you've ever heard something about logs or seen it on your calculator or even Desmos, logs are the inverses of exponential. And so that's what we're going to be talking about today. So as far as the parent function, our parent function is this function. Here's the symbols for it. It's log BA equals x. Okay? B is the base. So that number there is the base. X is the power. And I'll explain all this in just a second, and how it relates to the exponential. And A is the answer. Whenever you have a log tells you the power of an equation. Okay? If you ever hear about earthquakes and they talk about the Richter scale and how powerful the earthquake was, the Richter scale, you get that with logs. And this number right here is the power of that on that Richter scale. Okay, so that's where it comes from, sort of. First thing you need to know is that you can't take a log of a negative number. That means A will never be negative, because A is what you're taking the log of. Logs and exponentials are reflections of each other, as long as you're talking about on the y equals x, which means they are inverses, which is kind of what I showed you with that graph. We're going to do some more with this part right here in a minute, but we're going to look at the graphs of logs first. And I sort of already told you this is sort of what the graph's going to look like. It's going to kind of go up and level off, sort of like an exponential, but the inverse of it. We can graph this on Desmos. The log is at a weird place on Desmos, and so I want to show you that. When you go to the keyboard, if you go to Functions, and it's under Miscellaneous. So it's kind of at a weird place, but you see there's these two logs. Okay? We're going to use this one first. I'll explain what the other one is in a little bit, but we're going to use this one. And notice there's the 3 down here, and there's a place for me to put that 3, so I'm going to put the 3 right there. And then X. And then there's my graph. And just to kind of be a little bit more exact, it looks like there's a y-intercept at 1. So I'm going to put a y-intercept at 1. And it gets really, really close to this line, so just really close to it, and then it comes up. Now, I don't know, we've been talking about graphs quite a bit, and we've talked a lot about what happens whenever things, move right and left and up and down. Same thing happens with these two graphs. We can talk about it moving up, we can talk about it moving down, we can go right, and we can go left. And then you could use it on Desmos and graph it if you want to. We'll graph those in just a second. Let's just talk about the domain and range here. The domain, so because this graph gets really, really close to the y-axis, it doesn't ever touch the y-axis, but it's everything after that. So our domain is x is greater than 0, because it doesn't touch 0, but it's everything greater. Another way to write that is 0 to infinity, because it starts over here at 0, and then it goes to infinity. The range, it goes down forever, and then it goes up. It almost looks like it levels off, but it really doesn't. It just keeps going up forever. So the range is negative infinity to infinity, or you can say all real numbers. So when you have logarithmic form, this is logarithmic form, okay? This is exponential form. And what you do is you can rewrite it. So some of the questions will just say, rewrite this in either logarithmic form or exponential form, okay? And sometimes I've seen teachers, they start with the base. The base is that number right there. You go all the way to the other side of the equal, and then you come back to the answer. It's like this circle thing. And if that helps you to figure out what order to put it in, then you might need to do that. So here's the way that you write it. But you start with x, you go to b, so x to the b equals a. Okay? So x to the b equals a. And this answer right here, whatever the answer is always the power, like I said earlier. There are times that there won't be a number there where that x is. If there's not a number, it's understood to be 10. I know a lot of times we say that when there's not a number there, we understand that the base would be 1, but that's not the case here. The base is 10, and so we need to know that. Ln is another kind of log that you might see. Okay, it's called the natural log. And whatever happens with logs also happens with natural logs. The base, if you have a natural log, is called e. Okay, you know e, our exponential function that we talked about when we use PERT. Sometimes we might have to use an e, and e would be the base that's understood there. So we'll talk about that. Alright, so first thing we want to do is just change the functions from logarithmic form to exponential form. So we're just rewriting here. We're not really doing math, we're just like changing things. So you start with the little number, because that's always a base. You go on the other side of the equals, and then you go to the number that it's of. So this would be 2 to the third equals 8. When you're doing it, you do kind of look at what you have and decide, does that even make sense? Does it make sense that 2 to the third power is 8? Yeah, it does. So that would be correct. You won't always be able to make sense of it, but sometimes you will. Okay? So number 2. I'm going to start with the 4. I go 4 to the 2 equals 16. So it would be 4 to the 2 equals 16. So not a lot to do, just knowing what order to put things in. When you're doing these problems, you might see X's and A's and B's and all kinds of letters. It might not be written like this. They might have an A there and a C there or wherever. That's okay to happen that way. All right, the next one. 2 to the negative 1 equals a half. We're going to be talking a little bit about exponents. And whenever you have negative exponents, you do get a fraction for your answer, and we'll talk about that also. Alright, number 4, we talked about a log with no base has an understood base of 10. What that means is on this one that there's an understood 10 down here, even though I don't see it. Okay? And so if I want to rewrite that one, I'm going to start with 10. I'm going to go to 4 and then equal it to 10,000. So 10 to the 4 equals 10,000. The good things about 10, whatever power this is, that tells you how many zeros there are. I also told you whenever there's a natural log, Ln, there's an understood e. So even though I don't see that e, I know that that e is there. And it looks like I did not make up a good problem here because this is not going to be correct, but that's okay. We can still talk about it. E to the 5th equals 4. E to the 5th really doesn't equal 4, so I made up a bad problem. But I think it's good for you to be able to see what happens with that e. Okay, so going back the other way, we do the same thing. We want to write it with a log. And so this is x to the b equals a, and then this is the form of it. What I do here is I think about, okay, I know it's going to be something here, and then something there, and then something there. That's like the order, if I can get good at it. So I know that the base is 4, so 4 is the number that goes here. I know I'm raising it to the third power. The power always goes on the opposite side of the log. And whatever the answer is always goes beside of the 4. And then I could, like, the way that we just did those, how we did the little arrows, I could just check it. 4 to the third equals 64. Oh yeah, that's right. 4 to the third equals 60. So you can sort of check it to make sure that you did it right. Then I'll just go backwards with it. Okay, so look at the next one. Log. Okay, so think about the base. The base is the number that's being raised to the power. I know that goes here. I know the power goes over here. So 2 to the 5th equals what's here. So 32 is what's there. So 32 will go there. All right, let's do another one. The base is 3, so 3 comes down here. So 3 to the negative 2. The power always goes on the other side of the equals. And then 1/9 will go here. Okay, last one very quickly just to show you. This is a 10. Because that's a 10, you can put a 10 there, but you probably won't see the 10, so I'm not going to write the 10 since it's understood to be a 10. So there's an understood 10 right here. 10 to the second, so I know that the 2 will be on the other side of that. And then it'll equal 100, so there's 100 here. So even though my 10 there, I kind of wrote it lightly, but you probably won't see it if you're trying to do multiple choice. So when we're raising things to powers, we can just figure out what the power is. When you end up with fractions, you'll end up with negative powers. And when you end up with roots, you'll end up with fractions. And again, it's not a big deal. I will show you that you can do all of this on Desmos, but I wanted to just see that process. So when we get to the point that we're actually evaluating logs, what we want to do is we want to figure out the power that makes it true. So what you do first is you rewrite this using exponential form. So we're going to say 2 to what power, because we don't know it. 2 to what power is 16. Okay? So you rewrite it in exponential form with the x there, and then you try to figure out what x is. So we're saying in our mind, okay, what power do I raise 2 to that will give me 16? And if you think about multiplying 2 several times, well, it's going to be 4, I think. But here's how you can check it. You go to functions, you go to your log, and we're just going to put log 2 and then 16. And it tells me it's 4. Okay? I think it's important for you to think about what power you're raising it to and how to get the answer, but ultimately, Desmos will help you get the answer. Okay? So let's do another one. Here we have, I'm just going to equal it to x because we don't know it. We're saying 9 to what power is 9? Well, what power do you raise 9 to that will give you 9? 1. But again, we can check it on Desmos, make sure we're doing it correctly. Oh, let me keep the 9, that's nice. There we go. And so it gives me 1, so I know I did it correctly. Okay. What's understood to be the base on number 12? 10. So we're saying 10 to what power is 10,000. And I think I told you earlier, depending on how many zeros there are, that tells you what the power is. It's going to be a 4. Again, you can put it in here. You can, whenever it's log and there's no base, you can just press log. You don't even have to go to that function. Oh, you don't put commas, sorry. And so you get 4, which is what we thought the answer was. All right, look at number 13. Set that equal to x. Because that's how you're rewriting it to think about it. So we're saying 3 to what power